Hello, good evening, all of you. My name is Parth Joshi. I am a PhD student of Mechanical Engineering Department at IIT Bombay. I am a recipient of Prime Minister's Research Fellowship, and as a part of that of this fellowship, I have been given an opportunity to conduct live sessions uh, for the NPTEL course on Introduction to Mechanical Vibration. So I'll be meeting you every week. Uh, I'll be conducting live sessions for you. So the intention of conducting these live sessions is basically to help you understand the concepts better, to make the course more interesting and more engaging. Uh, so the plan is to conduct these live sessions with I'll be mainly covering uh, I'll be trying to solve some sample problems which will be similar to the kind of problems you would be solving in the weekly assignments, and I will also try to address any questions, any queries, any doubts that you have related either to the lectures or even with the assignments or any of the live sessions. So I'll be available to address any of your questions. So please feel free to reach out to me either in these live sessions, or also you can reach out to me through the discussion forum page of the course. So feel free to ask any questions, any doubts. So let us get started with the session. So in the first week of the course, these are the kind of concepts that were covered in the first week of the course content. So the first week included mainly the fundamentals of vibrations, the kind of applications, the kind of scenarios in which we encounter vibrations. Uh, so the also like the discussion is included where vibrations may be undesirable, as well as there are some applications where vibrations are actually useful. So all these applications have been discussed. Then there is a lecture on harmonic motion, which includes basically which explains the simple harmonic motion, and then addition of such multiple simple harmonic motions to get more complicated motions. And then the phenomenon of beats is discussed, wherein two harmonic motions with frequencies very close to each other, they are combined together. Then there is a lecture on Fourier series and harmonic analysis, so which discusses how can we express any periodic function as a sum of sine and cosine series. So and then these techniques of Fourier analysis have been described in detail. Then Professor Anil Kumar has also covered the general procedure for vibration analysis, which is basically, to summarize, it starts with mathematical modeling, where we extract the whatever desirable characteristics basically of the system in under consideration, which basically in the context of vibration analysis mainly deals with the mass properties, stiffness, damping, all these characteristics. And then we derive the governing differential equations, and then try to solve the governing differential equations using various methods, either analytical or numerical or And Professor Anil Kumar has also solved several numerical problems, which in his lecture, which cover all these different concepts that were discussed in all the lectures. So as you go through the course, so you may need to refer some books. So the lecture should be self-explanatory. Like the lecture should be sufficient to to help you understand all the concepts of vibrations. But if you think that you need to refer any book so as to understand any concept better, these are some books which I would recommend for you. So one is basically Mechanical Vibrations by S.S. Rao. Another book which is a classic book is Mechanical Vibrations by J.P. Den Hartog. And another book which I had referred during my undergraduate is Theory of Vibrations with Applications by Thomson and Dahle. And I had also referred to one book by A.P. French, Vibrations and Waves, so which is a nice book in the MIT Introductory Physics series. So it explains quite well in a very simple language and through very good illustrations all the basic concepts of vibration. So this should be a good introductory book for you to get started off to understand the basic concepts of vibrations. And then obviously Mechanical Vibrations by S.S. Rao is a comprehensive book and which deals with all the concepts and explains everything very well. It also has a lot of solved examples, and it has a huge collection of problems to solve. So that is a good book to refer definitely. So now let us move on to the assignment problems. So today I'll be basically discussing with you some of the solutions to some sample problems based on the content for the first week. So I have selected some problems which are based on the content that was covered in the week 1 lectures. So these are some simple problems which will help you understand some of these concepts better. So let us get started with the first question. So it asks whether what kind of a motion is harmonic motion. So as per the definition, harmonic motion is basically either a single frequency, like a periodic motion which includes a single frequency, or a combination of such simple harmonic motions of single frequencies. So harmonic motion is essentially periodic motion. So the correct answer to this question is option B, periodic motion. Now moving on to the next problem. So now let us move on to the next problem. The displacement of a particle undergoing simple harmonic motion. The displacement of a particle undergoing simple harmonic motion follows the equation y is equal to half sine pi into the bracket t by 3 plus 1/4, and where y is the displacement in centimeters and t is the time. So there was some problem with my screen sharing, but it has come up again. So yeah, so the second problem is basically the displacement of a particle undergoing simple harmonic motion follows the equation y is equal to 1 by 2 sine pi t by 3 plus 1/4, where y is the displacement in centimeters and t is the time. So in the problem, the maximum acceleration of the particle has been asked. So now how do we solve this problem? So for this, we have to note that how do we express any simple harmonic motion. So we can express any simple harmonic motion in this form. So let us say x is equal to a sine omega t plus phi. So here x can be said to be the displacement, same as let us say y, which is equivalent to y. So here a is basically the amplitude, omega is the natural frequency, and t is the time in seconds, and phi is basically the phase difference. So here if we compare the equation which is given over here, so y is equal to half sine t by 3 plus 1 by 4, so into pi. So it is sine pi t by 3 plus pi by 4 into half. So here the amplitude of this motion is half, the natural frequency is pi by 3, and the phase difference phi is pi by 4. So now, so we have been asked what is the maximum acceleration. So in simple harmonic motion, the restoring force is proportional to the displacement, and it acts in the direction opposite to the motion. So therefore the maximum acceleration in simple harmonic motion is given by, maximum acceleration is proportional to the amplitude and also proportional to the square of the frequencies. So the magnitude of the maximum acceleration is given by a into omega square, where a is the amplitude and omega is the natural frequency. So here it will be half into pi by 3 whole square, which is pi square by 9 into 2, which is pi square by 18. So here now pi square is about 9.81 and divided by 18, so it will be somewhat close to 0.5. So the correct answer to this question is 0.55. So this value of the expression pi square by 18, it works out to be about 0.55. So the correct answer to this question is option C. So now let us move on to the next question. So in the next question, it has been asked that two springs have a stiffness of 18 Newton per mm and 12 Newton per mm, and they are attached in series, and there is a mass which is suspended at the end of it. So the equivalent spring stiffness of the two springs has been asked. So for such questions, since there has been no figure that has been given, so we need to first construct the configuration of the system. So let us consider that we have such springs connected, suspended from the roof. So let us say there is a spring K1 and another spring which is attached to that in series, which has a stiffness of K2, and we have a mass M which is suspended at the other end of the spring. So for this problem, we first need to construct the free body diagram of the system. So let us start with the mass, the block of mass m first. So the mass m, on the mass m we will basically show all the different forces that will be acting on that. So the first force that will be acting will be its own weight mg, and there will be some tension in the spring. So now here we assume that basically the mass m is constrained to move vertically, and so there is no other motion. It has just, let us say, it's oscillating in this direction, in the vertical direction. So then the spring force and its weight will be the two forces that will be acting in the vertical direction. So now similarly we will draw the free body diagrams for the springs K1 and K2. So on the spring K2 we will have the same spring force Fs, and here also the same spring force Fs that is acting on the spring K2. Here we are assuming that the both the springs are massless, so the force acting at the ends of the spring will be in equilibrium. So the same force will be transmitted through the springs. Now we will similarly draw the free body diagram for the spring K1 as well, and it also has the same kind of a free body diagram. So let us say that the deflection in the spring K1 is delta 1, and the deflection in the spring K2 is delta 2. So now, as per the Hooke's law, as per the Hooke's law, for both the springs K1 and K2, so the spring force Fs is given by Fs is equal to K1 into delta 1, and the spring force for K2 is given by K2 delta 2. So if we replace these two springs by an equivalent spring, it will also transmit the same force Fs, and let us say it has an stiffness K equivalent, Keq, and let us say its deflection of the equivalent spring is delta Eq. So now, since the springs are in series, the total deflection of both the springs K1 and K2 combined together will be the deflection of the equivalent spring. So then delta Eq can be written as delta 1 plus delta 2. So now we use these expressions for the Hooke's law, and if we express the deflection in terms of the force and the stiffness, so Fs divided by K equivalent will be the expression for delta Eq, and similarly for delta 1 and delta 2 we can write delta 1 as Fs upon K1 plus, and delta 2 similarly as Fs upon K2. So now we got an expression in terms of the equivalent spring stiffness and K1 and K2. So now we can simplify this expression further. So therefore we observe that the spring force Fs is present on both sides, so we can cancel it. So therefore we get the expression for the spring equivalent spring stiffness. 1 by K equivalent is equal to 1 by K1 plus 1 by K2. So therefore K equivalent can be written as K1 K2 upon K1 plus K2. So now in this question we will get the equivalent spring stiffness. Here K1 has been given as let us say one of them is 18 and K2 is 12. Newton per mm. So we can substitute the values of K1 and K2 in this expression, and so we will get the expression for the equivalent spring stiffness. So that will be 18 into 12 divided by 18 plus 12. So which is 18 into 12 by 30. So which is equal to 7.2 Newton per mm. So this was the solution for the question. So let us now move on to the next question. So the next question is, so the expression for a harmonic motion is given in terms of the displacement, again as an expression for a simple harmonic motion in terms of amplitude, natural frequency and its phase difference is given. So we have again the expression in that form of A sin omega t plus phi. So here if we compare the expression that is given, so we will get that amplitude is equal to 12 units in mm, and the natural frequency omega is -25 and the phase difference is -π/4. So now it has been asked in the question, what is the time period for the motion. So the time period for the motion is given in terms of the angular frequency omega. So the time period, let us say t, is given by t is equal to 2 pi upon omega. So which is 2 pi upon 25. So which will work out to so it will work out to be about 2 pi upon 25. So it will work out to be about 2.2513. So the correct answer to our question is the option 0.2513. So now this was about the time period. So let us now move on to the next question. So in this question, this is about Fourier series expansion. So the general expression for a Fourier series for a function f of x has been given over here. So now the most important requirement of for the f of x, function f of x, is that the function f of x should be periodic to be able to express as a Fourier series. So that is one of the important requirements of for being able to express the function f of x as a Fourier series. So basically in the Fourier analysis, we decompose our function. We basically try to approximate the original function f of x by expressing it as a series of sine and cosine functions. We add together multiple sine and cosine functions, and we take a weighted sum of all these functions and try to approximate the basically the function, the periodic function f of x, using a series of cos and sine functions. So now here we have basically infinite number of sine and cosine terms, so added together so as to obtain the function f of x. So there are there are n number of constants a n and b n, that basically those are basically the weights, or so these are the constants a n and b n which need to be determined for in a Fourier series expansion. So to determine the values of values of a n and b n, we use an important property of the cosine and sine functions, which is orthogonality. So what does orthogonality mean? So if we consider so let us say if we consider that the function f of x has a period of L, and so we can write its Fourier series as fx is a naught plus so here for any function with with an arbitrary period of length L, we can write the general expression for the Fourier series in this way. So now to determine the values of the constants an and bn, we use the property of orthogonality of sine and cosine functions. So now if we consider the function cos n pi x by L and cos m pi x by L, and if we integrate the multiplication of these two functions over the interval minus L to L, then what the property of orthogonality of the sine and cosine function says that the value of this integral will be 0 when m is not equal to n, and the value of this integral is non-zero when m is equal to n. Similarly, we can have, so the sine function also has the same property. So the integral of sine n pi x by L into sine m pi x by L dx again, this integral will also be 0 when m is not equal to n, and it will be non-zero when m is equal to n. So this property is useful for us to determine the values of the expressions for to calculate the values of an and bn. So we get, using the property of orthogonality of the sine and cosine functions, we get the expressions for the values of an and bn. So these are given over here. So how do we get these values? What we do is that we basically in the Fourier series we multiply both the left hand side and right hand side by cos m pi x by L, let us say, and then we basically get that so all the other terms corresponding to the values where n is not equal to m, all of them will be 0, and only the terms corresponding to m is equal to n will be present, and then so the integral will essentially reduce to let us say so we will get for let us say if we have a function with an arbitrary period minus L, so we will get f of x into cos n pi x by L dx divided by integral minus L to L cos square n pi x by L dx. So value of the integral in the denominator, so we can calculate it to be so this integral will work out to be integral minus L to L 1 minus cos 2 pi nx by L into dx divided by 2. So therefore, the value of this integral will be, so it will be 2L by 2 minus, so the integral of cos 2n pi x over minus L to L will be 0 because of the periodicity of the cosine function. So the value of this integral will be L in the denominator. So the expression for an will be integral minus L to L f of x cos n pi x by L dx divided by L. Yeah, sorry again for the interruption. So we basically get the expression for an, which is multiplication of the function f of x into cos n pi x by L, or and similarly we will get an expression for bn, which is f of x integral minus L to L f of x into sine n pi x by L dx divided by L. So now we have the expressions for the values of the constants an and bn. So now the question that was asked is, what will be the values of an and bn when we have the f of x is either an even function or an odd function. So now let us consider the expression for an. So now an includes a multiplication of fx into cos n pi x by L. So the function cos n pi x by L is a even function. So cosine function is even because it is symmetrical about the y-axis. So if we try to plot the function cos x, so it will be something like this, so which is symmetrical about the y-axis. Whereas if we try to plot the function y is equal to sine x, it is anti-symmetric about the y-axis. So then that means that the function sine x is odd. So therefore, when the function f of x is even, so So what will happen is that uh, the multiplication of two even functions results in an even function. So when the function f of x is even, the value of this integral, so the multiplication of f of x into cos n pi x by l will result in an even function, and the value of this integral from minus l to l will be non-zero. And on the other hand, if the function f of x is odd, then the multiplication of f of x into cos n pi x by l, that will result in an odd function. So then, because of the property of definite integrals, so for an odd function, because of the so since the, let us say, the sine function over here, it is antisymmetric, so this area and this area are actually equal but and opposite in sign. So when we integrate the sine function from, let us say, minus pi to pi, it will add up to 0. So therefore, similarly, we have the integral minus L to L, so then that will also become 0 when the function f of x into cos n pi x by L, that is odd. So therefore, basically, essentially, when f of x is odd, an will be 0. So an is non-zero when f of x is even, and an will be 0 when f of x is odd. Similarly, if we go by the same argument for Bn, so when the function f of x is even, then the multiplication of f of x into sine pi n pi by pi x by L will result in an odd function when f of x is even. So then for an odd function, then again the integral from minus L to L will be 0 by the same argument. So therefore, Bn will be 0 when f of x is even, and Bn will be non-zero when function f of x is odd. So why it will be non-zero? Because so when the function f of x is odd, and since sine n pi x by L is also odd, so therefore the multiplication of f of x into sine n pi x by L, that will result in a even function. So multiplication of two odd functions will be even. So therefore this integral will be non-zero, and therefore Bn will also be non-zero. So when the function f of x is odd. So now let us move on to the next question. So the next question asks like, so there are two simultaneous harmonic motions x1 and x2 that are given. So the question is, what is the maximum and minimum amplitude of the combined motion, and what is the frequency of beats? So here now, if we observe carefully, there are two different motions x1 and x2. They have different amplitudes and different frequencies. So how do we describe the combined motion of these two motions x1 and x2? We will simply add x1 and x2, x1 plus x2, which will be 5 sine 38t and 3 sine 36t. So that will be the resultant motion. Now to add up this into a simplified expression is a bit tricky. So the combination of this motion, so it will it will have a resultant motion whose amplitude is varying with time and the phase is also varying with time. So therefore uh, so there will be some instances where the motions x1 and x2 will be in phase, and certain scenario situations, certain instance when the motions x1 and x2 will be out of phase. So let us say the amplitude of x1 is, let us say, a1, and the amplitude of x2 is, let us say, a2. So now there will be some scenarios when these two amplitudes will be in phase. So then the maximum amplitude that will be possible will be the sum of a1 plus a2, which is 5 plus 3, which is 8. So that will be the maximum possible amplitude. Similarly, the minimum possible amplitude will be a1 minus a2, which will be 5 minus 3, which is equal to 2. So that will be the minimum possible amplitude when both of them are out of phase. Now the next question is, what is the frequency of beats? So the frequency of beats, let us say FB, is given by the difference between the frequencies f1 and f2. So let us say it is f1 minus f2, the absolute value of that. So here the angular frequency of the first motion x1 is omega 1. So here omega 1 is equal to 38 and omega 2 is equal to 36. So now the frequencies, how do we find the frequencies f1 and f2? We basically use f1 is equal to 2 pi upon omega 1 and f2 is 2 pi upon omega 2 . So now if we substitute the values of omega 1 and omega 2, we will get the frequency of beats as fp is 2 pi upon 38 minus 2 pi upon 36, the absolute value of this, which is pi by 19 minus pi by 18, the absolute value of this. I'm sorry, so there is a small mistake. So the frequency of beats is given by absolute value of 2 pi upon omega 1, which is 38, minus 2 pi upon 36, so that will be the frequency of beats for this see these two motions. So the frequency is actually omega by 2 pi. So the frequency of beats will be given by omega 1 by 2 pi minus omega 2 by 2 pi. Yeah, so it will be 38 minus 36 divided by 2 by 2 pi. So it will be 2 by 2 pi, which is equal to 1 by pi. So this will be the value of the frequency of beats. So the next question is about torsional vibrations. So for that we need to understand the governing differential equations for torsional vibrations. So we can let us say for any shaft, let us say if we have a twisting moment T, then as per the theory of torsion, it is equal to the twisting moment is given by minus g theta by L, where g is basically the modulus of rigidity and L is basically the length of the shaft, and the twisting moment, it is basically because it is opposite to that, so the twisting moment is given by j theta double dot, and since the twisting moment is opposite to the direction of the twist, so therefore j theta double dot, so where j is basically the polar moment of inertia for the cross section. So therefore for the torsion of a circular shaft, we can write so J is basically the polar moment of inertia. So the torsional stiffness of the shaft is basically the torque per unit twist. So T by theta is minus G into J by L. So here, so we have the cross section of the shaft as, so it has an internal radius of 15 mm. Let us call it as R1 is 15 mm, and R2 is, let us say, the external radius. So let us call it this as R1 and this as R2. This 30 mm. So what is the value of the polar moment of inertia? So it will be, so the value of J is for the for a shaft is basically pi d to the power 4 by 32, or alternatively, so in terms of the radius, it is pi r raised to 4 by 2 for a solid circular shaft. So now, since here we have an annular circular shaft, we subtract the polar moment of inertia due to the internal hole. So therefore, so for the annular shaft we can write the that will be, so the expression for the polar moment of inertia J for the annular shaft. Then we are also given the value of G, which is 210 gigapascal, and its length is also given as 2 meters. So now if we try to solve this problem, so let us, here we have R1 is equal to 15 mm, so it is 15 by 1000 meters, and its value of R2 is 30 mm, so which is equal to 30 by 1000 in meters, so which is 0.03. The value, so therefore the value of J is given by pi into the value of R2 to the power 4 minus the value of R1 to the power of 4 divided by 2. So this will be the value of J in terms of meter raised to the power 4. Then we have the value of G, which is 210 gigapascal. So 210 into 10 to the power 9, and the value of the length L is given by 2 meters. So the torsional stiffness K is given by G into J divided by L. So which is about 1 to 125. So if we divide this by 1000, which is 125, about 125 kilonewton per meter, or alternatively 125 Newton per mm. So the correct answer to this question is T, 125 kilonewton meter per area. The option B. So now moving on to the next question. So we have been given several springs that have been connected in series and parallel. So we have to find out the equivalent stiffness of the system over here. So here we have two springs. So in the bottom we have two springs in series and these two springs and these two springs, they are in parallel, and these two and the equivalent spring stiffness of these two springs which has been highlighted in blue, that is in parallel with the equivalent stiffness of these two in series. So the blue ones are in parallel. So for springs in parallel, let us say there are two springs in parallel. So K1 plus K2 will be the equivalent stiffness of two springs which are in parallel, and for springs in series, the K equivalent is given by K1 K2 upon K1 plus K2. So here for the two springs in series which have stiffness of K, it will be K into K divided by K plus K, which will work out to K by 2. And for these springs which are in parallel, we will get K equivalent is equal to K plus K, which is equal to 2K. So now the system will look like as follows. So we will have a spring with stiffness 2K in parallel with another spring with stiffness K by 2, and in series with that will be another spring with stiffness 2K, and a force that is applied to the system. So now we again apply the same logic. So we basically find out the equivalent stiffness of these two springs in parallel, which will be, so the K equivalent for this system will be 2K plus K by 2, which is equal to 5K by 2. And the spring with stiffness 5K by 2 and 2K, so we have K1 is 5K by 2 and K2 is 2K, and these two are now in series. So now the new K equivalent will be 5K by 2 into 2K divided by 5K by 2 plus 2k. So then k equivalent will be (10k) divided by 5k plus 4k, or 10k by 9. So the equivalent stiffness of this system will work out to be 10k by 9. So let us now move on to the next problem. So here it has been asked about the resultant displacement of 3 harmonic motions. So for that, let us first see the equivalence between the simple harmonic motion and circular motion. So what is the relation between that? So let us consider that a particle, let us say, is moving around a circle with let us say radius a, and it is moving around a circle. Let us say this is the particle, and it is moving around a circle with an angular frequency, let us say omega. So now if we find out the projection of the particle on to the x and y axis, so what would we get? So we would get, so the angle made by the particle, let us say if it starts from at this point, so from the so let us say if we assume that the particle starts over here, when it makes an angle 0 with the x-axis, and in time t it would have moved, it would have rotated by an angle of omega t, considering that it moves with a constant angular velocity omega. So then the projection of the motion of this particle on the x-axis, so basically this is given by a cos omega t, and similarly if we consider the projection on the y-axis, it will be given as a sin omega t. So basically we know, so what we understand from this is that the projection of a particle moving in a circle, so its projection on the x and y axis are basically simple harmonic motions of the nature of sin omega t and cos omega t. So cos omega t if we project it onto the x axis, and sin omega t, a sin omega t, if we project it onto the y axis. So now here we have 3 different harmonic motions, x1, x2 and x3. Now what we have been given is that we have to find out the resultant of x1 plus x2 plus x3. So now how do we determine that? So we would again use this same concept of representing. So let us consider like 3 different particles now. So the first particle is the one which is, we will number it as 1, second particle over here as 2, and 3 over here. So now x2 is given by a sine omega t plus 2 pi by 3. So now the first motion x1 will be given by the projection of this particle onto the y-axis, and x2 is given by a sine omega t plus 2 pi by 3. Which therefore, if we consider an additional angle of 2 pi by 3 made with this radius, so that will be, so this entire angle will be omega t plus 2 pi by 3. So now if we project the motion of this particle onto the y-axis, it will again be a sine omega t plus 2 pi by 3. And similarly, if we consider another third particle which makes an angle 4 pi by 3 with this radius, so let us say that this angle is, let us say, 4 pi by 3. So now basically we have three different particles. So the first one is given by a sine omega t. For the second particle's motion is given by a sine omega t plus 2 pi by 3, and we get the third particle we can locate over here, which makes an angle of 4 pi by 3 with this radius. So again the projection of this particle's motion onto the y-axis will be a sine omega t plus 4 pi by 3. So 2 pi by 3, so if we convert it into degrees, it is makes an angle of 120 degrees, and 4 pi by 3 will be similarly 240 degrees. So if you observe that these three particles are separated by 120 degrees, which means that they are symmetric with respect to the origin. So the first particle, so the angle between the first particle and the second one is 120 degree. Similarly, the angle between the second and third one is again 120 degree, and between the third one and the first one is also 120 degree. So we see that the system will be always symmetric. And now, because of the symmetry, these particles will always be in this kind of a symmetric configuration. They will always be separated by an angle of 120 degrees with respect to each other. And so by that, if we try to project, so the resultant motion of these three particles rotating symmetrically with respect to the origin, and so the addition of the projections of these three particles onto the y-axis will actually add up to 0 because of the symmetry of the system. So no matter what is the value of omega t, so at any instant of time, they will be always symmetric with respect to the origin, separated by 120 degree, and their resultant motion will always be 0. Now we can also analytically verify this by using the by adding the expressions of sine omega t plus 2 pi by 3 and sine omega t plus 4 pi by 3. We will arrive at the same conclusion, but this is how we can graphically also arrive at the same conclusion by using the argument of symmetry. Now we Now we come to the last question in the assignment. So we have a cantilever beam which is made up of an alloy. It has a Young's modulus of elasticity of 72 gigapascals, and it is given that it is loaded transversely at its free end. So let us try to draw a figure of a cantilever beam. So it is loaded transversely at its free end. So let us show a force. Let us say a force F, which is acting transversely at the free end, and this is the fixed end of the cantilever. The length of the beam, let us say L, is 750 mm. The beam has an annular cross section with inner and outer diameters. They have been given. So let us draw an annular cross section. So it has two, so the diameters, let us say D1 and D2. So D1 is the outer diameter and D2 is the inner diameter. So it has been given that D1 is 120 mm and D2 is 110 mm. So what we need to do here is that we need to find out the stiffness of this beam. Now from the Euler-Bernoulli beam theory, we know that the deflection at due to a concentrated force at the tip of a cantilever beam, let us say delta, that is the deflection, that is given by FLQ by 3 into E into I, where E is basically the Young's modulus and I is the moment of inertia of the cross section. So the moment of inertia about the plane of bending. So the plane of bending is basically the cross section of the beam, which is the annular cross section. So the value of Young's modulus has been given to us, that is 72 into 10 to the power 9. So what we have to find is the value of I. So how do we find out the value of moment of inertia of this cross section? So for that we can find out we already know the expression for polar moment of inertia of the cross section. So basically the value of J will be given by pi d1 to the power 4 minus t2 to the power 4 by 32. So that will be the polar moment of inertia of the cross section. Now since this is a circular cross section and it is symmetric about its own axis, so let us say this is the axis, so the cross section is now symmetric about its axis. So if we let us say if we consider an xyz coordinate system, and so let us say this is the cross section. So the polar moment of inertia is basically the moment of inertia of the cross section about the z axis. So by the perpendicular axis theorem, we know that Iz can be expressed as the sum of the moment of inertia of the cross section about the x axis and the y axis. So now, because of the symmetry of this cross section, Ix will be equal to Iy. So it will be 2Iy or 2Ix, or let us say 2I. So I will be j by 2, which is pi into t1 to the power 4 minus t2 to the power 4 by 64. So this will be the expression for the moment of inertia of the cross section. So we now know the deflection of the cantilever beam in terms of the Young's modulus and the moment of inertia of the cross section. Its length is known. So now we have to find out the stiffness. So the stiffness is given by the force per unit deflection, F by delta. So now using this expression, we will get that the stiffness is given by 3EI by L cube. So which is 3E by L cube into pi t1 to the power 4 minus t2 to the power 4 by 64. So now in this problem, we have T1 as 120 mm. So in terms of meters, it is 120 by 1000. We have T2, which is 110 mm. So it will be 110 by 1000 or 0.11 meters. We know the value of E, which is 72 into 10 to the power of 9 pascals, and we know the length of L, which is 750 mm or 0.75 meters. So the value of J is pi into d1 to the power 4 minus d2 to the power of 4 divided by 32. So this is the value of J, and the value of I will be J by 2. So which is the value of J by 2, and so therefore the stiffness K, which is F by L, so which is 3 into 3EI by L cube, which is equal to 3 to E into I divided by length cubed, so it will be so the stiffness will be 150.18 kilonewton per meter. So this is how we can solve some of these problems related to the week 1. So we have gone through some of the problems which are related to basic harmonic motion. How do we represent any harmonic motion in terms of its angular frequency, in terms of like as a sin omega t plus phi. So we discussed how we can calculate the natural frequency, amplitude and phase difference. So based on in terms of the amplitude, natural frequency and phase difference, we can write the expression for any simple harmonic motion. Then we discussed how we can find out the equivalent stiffness in different systems. We derived the expressions for the equivalent stiffness in series and parallel. So we also discussed how to calculate simple quantities like the time period and also the natural and the frequency in terms of the angular frequency. Then we also discussed about how the constants in a Fourier series change depending on the nature of the function, whether if it is odd or even. We discussed how it affects the value of an and bn. Then we discussed about a problem in which we have been given two different harmonic motions, and if we combine them together, what will be the maximum and minimum possible amplitudes, what will be the frequency of beats. Then we also studied in torsional vibrations, how do we basically find out the torsional stiffness of the shaft. It will be G into J by L, so that will be the torsional stiffness, and we basically calculated the value of the torsional stiffness for this shaft which is given. Then we found out what is the equivalent stiffness of different spring, the spring mass system, system. So different springs in series and parallel, we found out the equivalent spring stiffness. And then we also found out like if we have different harmonic motions, and so because they have same amplitude and because of the symmetry of the problem, the phase difference between them is 120 degrees, so all of them are spaced symmetrically with respect to the origin. So therefore the resultant motion of these three motions together, combined together, will be 0. And finally then we calculated, like for a cantilever beam which has an annular cross section, so we derived the expression for the moment of inertia of its cross section about the axis of bending, and then we calculated the resulting stiffness of the beam, so which works out to be about 153 kilonewton per meter. So that was about uh, the uh, the assignment problems for this first week. So if you have any doubts, any questions, any concerns, so you can reach out to me through the discussion forum of this course. So this session is being recorded and you will be able to watch it later on NPTEL website. So I hope you find all these live sessions useful. So I will see you next week in the Friday of this week. Thank you.